Hi, this lecture reviews the 3D rendering pipeline implemented by current GPUs. Ray tracing processes each pixel independently, thus it may repeat calculations that could be reused in other pixels. Consequently, ray tracing is slow. It is difficult to render complex animated scenes with ray tracing at high frame rates. The goal of incremental rendering is speed, and it sacrifices everything for it. To obtain an image quickly, it solves many problems for regions larger than a single pixel. This region is usually a triangle of the scene. It gets rid of objects that are surely not visible via clipping. Most importantly, it executes operations in appropriate coordinate systems, where this particular operation is simple. Moving object from one coordinate system to another requires transformations. As we cannot transform all types of geometry without modifying the type, we approximate all kinds of geometry with triangles. This process is called tessellation. Incremental rendering is a pipeline of operations starting at the model and ending on the image. Objects are defined in their reference state, also called modeling coordinates. First, surfaces are approximated by triangle meshes. Then the tessellated object is placed in the world, setting its real size, orientation, and position. Here, different objects, the camera and light sources meet. Ray tracing would solve the visibility problem here, but incremental rendering applies a transformation to find a coordinate system where it is trivial to decide whether 2 points occlude each other, and projection is also simple. This coordinate system is the screen coordinate system where rays are parallel with axis z, and a ray has a pixels x-y coordinates. To transform the model from world to screen space, first we execute the camera transformation, which translates and rotates the scene so that the camera is in the origin of the coordinate system and looks at the -z direction. Note that the negative sign is due to the fact that we prefer right-handed coordinate systems. In the camera coordinate system, projection rays meet in the origin. So to simplify this, we distort the scene together with objects in a way that projection lines or rays will be parallel to each other. This space is called normalized device space and also called clipping space because clipping happens here. Finally, we take into account the real resolution and objects are transformed to screen space. Tessellation of a parametric surface basically means the evaluation of the surface equation in parameter points that are placed regularly by a grid. Those points form a triangle, which are neighbors in parameter space. To obtain the shading normals, the cross product of the partial derivatives of the parametric equation is also computed at the sample points. The triangles of the parameter space can be visited row by row. Vertices of a single row are conveniently organized in a triangle strip. To get the normal vector of a parametric surface, we can exploit isoparametric lines. Suppose that we need the normal vector at a point associated with parameters U star and V star. Let us keep U star fixed, but allow V to run over its domain. This function is a curve. As it always satisfies the surface equation, this curve is on the surface, and when V equals V star, this curve passes through the point of interest. We know that the derivative of the curve is always tangent to the curve, so the derivative with respect to V at V star will be the tangent of the curve at this point. Consequently, it will be in the tangent plane. Similarly, the derivative with respect to variable u will always be in the tangent plane. The cross product results in a vector that is perpendicular to both tangents, so it will serve as the normal vector of the surface at that particular point. The tessellation is done on the CPU with our C++ program. The tessellated triangle mesh is copied to the GPU and assigned to a vertex array object. So the general base class of triangle meshes is the geometry that stores the VAO and the number of vertices. In its constructor, the VAO is bound and is made active. Param surface is the special type of geometry representing parametric surfaces. All parametric surfaces are similar in how they should be tessellated. The process should decompose a unit square into rows and columns and visit vertices row by row. A single row forms a GA triangle strip. Vertices are stored in the position of the vertex and the surface normal of the surface here, and also the corresponding parameter pair used as texture coordinates. These data are encapsulated in the vertex data structure. When the vertex data object is computed, we need a particular definition of the parametric function which is not available on this abstract level. So here we define a pure virtual function called eval or evaluation that should be specified in classes derived from this param surface base class. The creation of the surface data on the GPU happens in the create function. When the param surface is drawn, the VAO is activated again, since other VAOs may become active between the construction of this object and its drawing. Then the VAO is drawn, stating that its vertices define a triangle strip in each row of the tessellation structure. Recall that we have activated the VAO and then this create function is called. Now its corresponding data stored in a single VBO vertex buffer object, which is created here. If the parameter space is decomposed to n columns and m rows, then we have n number of strips and m plus 1 multiplied by 2 number of vertices. The VBO is generated and bound. Then it is filled up by calling the generate vertex data function on the vertices, one by one, visiting vertices in the fashion suggested by the triangle strip structure. In the GPU, vertex shader input register number 0 will get the position, register number 1 the normal, and register number 2 the UV parameter pair of particular points. The construction of a particular parametric surface means the definition of this evaluation function, which is just the implementation of the parametric equation, in addition to computing the normal vector. So, for example, if we consider the sphere as an example, this virtual function should be implemented according to the equations of the sphere. Another example is the waving flag that is modulated by a sine wave. As stated, the normal vector is just the cross product of the two partial derivatives of the parametric function. Again, only the evaluation function needs to be implemented on this level, which assigns the position and the normal vector to parameter pair u and v. Using the modeling transformation, the object is mapped to vert coordinates. Recall that the transformation of the shading normals requires the application of the inverse transpose of the 4x4 modeling transformation. Or if the normal is part of a column vector, we should multiply it with only the inverse. From vert coordinates, we go to camera space, where the camera is in the origin and looks at the -z direction. The transformation between vert and camera coordinates is a translation and a rotation. After camera transformation, the next step is the perspective transformation, which distorts the object in a way that the original perspective transformation or projection will be equivalent to a parallel projection of the distorted objects. This is a non-affine transformation. so it will not preserve the value that is equal to 1 in the fourth homogeneous coordinates. The three transformation matrices, the modal, view, and the projection or perspective transformation matrices, can be concatenated. So a single model view projection or MVP transformation takes the objects directly from modeling space to screen space. Modeling transformation sets up the object in the virtual world. This means scaling to set its size, then rotation to set its orientation, and finally translation to place it at its position. All three transformations are affine and can be given as a homogeneous transformation matrix. Concatenating these matrices, we obtain a single modeling transformation matrix, which maps the object from its reference state to its actual state in world coordinates. The definition of the camera transformation depends on the parameters of the camera. In computer graphics, the camera is the eye position that represents the user in the virtual world and a window rectangle that represents the screen. It is often more intuitive to think of the camera as being similar to a real camera. A real camera has a focal point or pinhole where the lens is and the planar film where the image is created in a bottom-up position. In fact, this model is equivalent to the model of the user's eye in the screen, just the user's eye should be imagined in the lens position and the film mirrored onto the lens of the screen. So in both cases, we need to define a virtual eye position and a rectangle in 3D. The eye position is just a vector in world coordinates. The position of the window is defined by the location of its center, which is also called look-at point or view reference point. We assume that the main viewing direction, that is between the eye and the look-at point, is perpendicular to the window. To find a vertical direction of the window, a view-up vector needs to be specified. If it is not exactly perpendicular to the main viewing direction, then only its perpendicular component is used. The vectors defined so far specify the window plane and orientation, but not the size of the rectangle. To set the vertical size, the field of view angle is given. For the horizontal size, the aspect ratio of the vertical and horizontal window edge sizes should be specified. Objects being very close to the eye are not visible and leads to numerical inaccuracy. So we also set up a so-called front clipping plane that is parallel to the window and ignore everything that is behind this plane. Similarly, objects that are very far are not visible and may lead to numerical representation problems. So we also introduce a back clipping plane to limit the visible space of the camera. Our goal is to transform the scene from world coordinates to screen coordinates, where visibility determination and projection are trivial. This transformation is built as a sequence of elementary transformations, but we shall execute all transformations at once as a single matrix vector multiplication. First, we apply a transformation for the scene, including objects and the camera, that moves the camera to the origin and rotates it to make the main viewing direction be axis minus z and the camera's vertical direction be axis y. To find such a transformation, we assign an orthogonal basis to the camera, so its first basis vector u is the camera's horizontal or right direction. The second v is the camera's vertical or up direction, and the third w is the opposite of the main viewing direction. We reverse its direction in order to make the system right-handed. Vector w can be obtained from the main viewing direction by a simple normalization. The application of normalization to get v from the view up vector is also tempting, but simple normalization would not guarantee that basis vector v is orthogonal to basis vector w. So instead of directly computing v from view up, first we obtain u, the right vector that is orthogonal to both w and the view up vector. Then v is computed indirectly through w and u to make it an orthogonal system. The transformation we are looking for is a translation, then a rotation. The translation moves the eye to the origin. The translation has a simple homogeneous linear transformation matrix, which is here. Having applied this transformation, the orientation should be changed to align vector w with axis z, vector v with axis y, and vector u with axis x. Although this transformation is non-trivial, its inverse that aligns axis x with u, axis y with v, and axis z with w is straightforward. So we are looking for this transformation, and the inverse just maps vectors back. Its basic idea is that rows of an affine transformation matrix are the images of the three basis vectors and the origin respectively. So the transformation of x, y, z to u, v, w is the matrix that contains u, v, and w as row vectors of a 3 minor matrix of a 4 times 4 transformation matrix. As we need the inverse of the transformation, this matrix should be inverted, so we write a -1 here. Such matrices are orthonormal matrices, so they are easy to invert because their inverse is equal to their transpose. In camera space, the camera is in the origin and the main viewing direction is axis -z. The normalization step distorts the space to make the viewing angle be equal to 90 degrees. This is a scaling along axis y and x. Considering scaling along axis y, before the transformation, the top of the viewing pyramid has y coordinate that is equal to the distance of the back clipping plane multiplied by the tangent of the half of the field of view angle. And after transformation, we expect it to be equal to BP. So the y coordinate must be divided by tangent of the half of the field of view angle. The transformation or the scaling of the x coordinate is similar, just the aspect ratio should be also considered. Perspective transformation makes the rays meeting in the origin be parallel with axis z, that is, meeting at infinity. Additionally, we expect the viewing frustum to be mapped to an axis-aligned cube of corner points -1, -1, -1, and +1, +1, +1. There are infinitely many solutions for this transformation problem. However, only those solutions are acceptable which map lines to lines and consequently triangles to triangles, since when objects are transformed, we wish to execute the matrix vector multiplication only for the vertices of the triangle mesh and not for every single point, since there are infinitely many of them. Homogeneous linear transformations are known to map lines to lines, so if we can find a homogeneous linear transformation, that can do the job. To find a transformation matrix, we consider how a ray should be mapped. A ray can be defined by a parametric equation here, where coordinate z is the free parameter and mx and my are the slopes with respect to x and y. We expect this line to be parallel with the axis z star after the transformation. So, in order to distinguish the original coordinates and the new coordinates in the transformed coordinate system, we denote the axes by x star, y star, and z star. In normalized camera space, the slopes are between -1 and 1. We expect this line to be parallel with axis z star after the transformation, so its x and y coordinates should be independent of z. As x and y must also be in the interval of -1 and 1, for the transformed line x star is just mx, and the y star is just my, and z star is a free parameter. The mapping from the original line to the transformed line cannot be linear in Cartesian coordinates, but is linear in homogeneous coordinates. So we are looking for a linear mapping from x, y, z 1 to x star, y star, z star 1, which is expressed in this form. To make it simpler, we can exploit the homogeneous property of homogeneous coordinates, which means that the represented points for coordinates can be multiplied by the same scalar. We are still referring to the very same point. So let this scalar be -z. Our goal is to find a linear mapping between this vector and that vector. Homogeneous linear transformation is a 4x4 matrix, that is 16 scalars or numbers, which need to be found. The requirement is that for an arbitrary mx, my, and z, when multiplying this with the 4x4 matrix, we get this resulting vector. The first two elements of the vector are kept for arbitrary mx, my, z, which is possible if the first two columns of the matrix are 1, 0, 0, 0 and 0, 1, 0, 0. The fourth element of the result is -z, independently of the values of mx and my, which is again possible if the fourth column is 0, 0, -1 and 0. We are left with only the two unknown parameters of alpha and beta in this matrix. They can be found by considering the requirement that the entry point, that is the intersection of the ray and the front clipping plane, should be mapped to z star equals -1, and the exit point should be mapped to z star equals +1. So we establish an equation for the unknown alpha and beta parameters, solve it, and eventually we can express the alpha and beta parameters with the front clipping and back clipping distances. Note that the expression of transformed z star coordinate is a function of z, which is nonlinear. We knew it from the very beginning that it cannot be linear. This function is a 1 per x type function and a hyperbolic function. Recall that such functions change quickly where z is close to 0, but their slope is very small if z gets large. To determine visibility robustly, the difference of the z star values for 2 points must be computed. So this difference should be large enough to decide robustly on the visibility. If we have 2 points for which z is small, then after substituting their z values into this hyperbolic function, the z star values will be quite different. But this is not the case when z is close to the back clipping plane and the back clipping plane distance is big, because their difference disappear or almost disappear after the transformation. As a conclusion, as the slope of this hyperbolic function can be expressed in this way, never specify front clipping and back clipping distances in a way that the ratio of FP and BP is too small, because that will result strong numerical inaccuracies. And on the image we will see it as objects that are otherwise occluded showing up on the screen. The phenomenon is called z-fighting. Normalization and perspective transformation are usually combined, and the composed transformation is set directly. The composed transformation has this transformation matrix. It is worth noting that this transformation sets the force homogeneous coordinate to the negative z coordinate evaluated in camera space. It is also notable that this transformation maps the eye, which is the origin before the transformation, so it can be expressed as 0, 0, 0, 1 in homogeneous coordinates to the ideal point of axis z. So the eye will go to infinitely far. Our 3D camera class stores the parameters needed to define a camera and implement two transformation functions v and p. Transformation v is the view transformation that takes the point from vert space to camera space, and transformation p is the projection or perspective transformation that takes the point from camera space to normalized device space. Transformations are set on the CPU but are applied to points by the GPU. Transformations are uniform parameters of the vertex shader, which are set from the CPU program and used by the vertex shader. We always need the MVP model view projection transformation, which is the concatenation of the model, view, and projection transformations. This transformation transforms the point from its modeling space to normalized device space, and the GL position output register should be filled up with the normalized device coordinates of the processed point. If illumination is also computed in the vert coordinate system, objects should be transformed there as well. For points, we need to apply the modeling transformation. For normal vectors, the inverse of the same transformation, and we should handle normal vectors as column vectors standing on the right-hand side of the matrix during multiplication. Clipping must be done before the homogeneous division, preferably in a coordinate system where the clipping region has the simplest shape. The optimal choice is the normalized device space where the view frustum is a cube. However, clipping must be done before the homogeneous division. This might be surprising, but becomes clear if we consider the topology of a projective line and the interpretation of a line segment. A projective line is like a circle. The ideal point glues the two ends of the line. As on a circle, two points do not unambiguously identify an arc because there are two possible arcs. On a projective line, 2 points may define two complementary line segments, this one and that one. To resolve this ambiguity, we specify endpoints with positive force homogeneous coordinates and define line segment as a convex combination of the two endpoints. If the force coordinates h are positive for both endpoints, then the interpolated h cannot be 0, so this line segment doesn't contain the ideal point. Recall that we can recognize a point to be ideal if its force homogeneous coordinate is equal to 0. Affine transformations usually do not alter the force homogeneous coordinate, so normal line segments remain normal. Perspective transformation may map a line segment to a line segment that contains the ideal point, which is clearly indicated in the different signs of the force homogeneous coordinates of the two endpoints. So, if the two h coordinates have the same sign, then the line segment is normal. If the two h coordinates have different signs, then the line segment is wrapped around, so it contains the ideal point and we would view it as two half-lines. One way to solve this problem is to clip away everything that is behind the front clipping plane before applying homogeneous division. Because homogeneous division would eliminate that extra information. We need solid rendering, which produces filled polygons and also considers occlusions. Many polygons may be mapped onto the same pixel, so we should find that polygon which occludes the others, that is, which are the closest to the eye position. This calculation is called visibility determination. We have to emphasize that visibility is determined in screen coordinates, where rays are parallel with axis z and x and y coordinates are the physical pixel coordinates. We made all the complicated looking homogeneous linear transformations just for this, to calculate visibility and projection in a coordinate system where these operations are very simple. There are many visibility algorithms. The literature classifies them as object space, also called object precision algorithms, and screen space, also called discrete or image precision algorithms. Object space visibility algorithms find visible portions of the triangles or polygons in the form of triangles or polygons independently of the resolution of the image. So it means clipping those parts of the triangles or polygons that are eventually visible. Screen space algorithms or image precision algorithms, on the other hand, exploit the fact that the image has finite precision and resolution and determine the visibility just at finite number of points, usually through the centers of the pixels. We call that ray tracing belongs to the category of image precision algorithms. First, an object space method is presented, which gives only partial solution. Assume that the triangle mesh is a boundary of a valid 3D object. In this case, we can see only one side or face of each boundary polygon. The potentially visible face is called front face. The other face or side where the polygon is glued to the object is called back face. A back face is never visible since the object itself always occludes it. So when a polygon shows its back face to the camera, we can simply ignore it, since we know that there are other polygons of the same object which will occlude it. To help the determination whether a face is a front face or a back face, we use a coding scheme that must be set during the modeling of the geometry or during the tessellation process. In theory, triangle or polygon vertices can be specified either clockwise or counterclockwise. Let us use this ordering to indicate whether a face is glued to the object. For example, we can state that vertices must be specified in clockwise order when the object is seen from outside, that is, when we see a front face of the polygon. Computing the geometric normal with this formula, the clockwise order means that the normal vector n will point towards the viewer. As in screen coordinates, the viewing rays are parallel with axis z, it is easy to decide whether a vector points towards the viewer. Simply, the z-coordinate of the normal vector must be negative. With backface culling, we can get rid of the surely non-visible polygons, which always helps. However, front faces may also occlude each other, which should be resolved by another algorithm. Still, backface culling is worth applying since it roughly halves the number of potentially visible polygons at a very little added cost. And now let us meet the far most popular visibility algorithm of incremental image synthesis. This is called the Z-buffer algorithm. Ray tracing considers pixels one by one, and for a single pixel it checks each object for the intersection while always keeping the first intersection found so far. In incremental rendering, we would like to exploit the similarities of different points on an object, typically on a triangle. So instead of processing every pixel independently, we take an object-centric approach. So let us swap the order of the for loops of ray tracing and take triangles one by one for a single triangle, find visibility rays intersecting it, always keeping the first intersection separately in every pixel. As all pixels are processed simultaneously, instead of a single minimum ray parameter, we need to maintain as many ray parameters as pixels the viewport has. In screen coordinates, the ray parameter, or in other words the distance of the intersection, is represented by the z-coordinate of the intersection point. Therefore, the array storing the ray parameters of the intersections is called the z-buffer or the depth buffer. The z-buffer algorithm initializes the depth buffer to the largest possible value, since we are looking for a minimum. In screen coordinates, the maximum of z-coordinates is 1, because backface clipping happens here. The algorithm takes triangles one by one in an arbitrary order. A triangle is projected onto the screen and rasterized. That is, we visit those pixels that are inside the triangle's projection. At a particular pixel, the z-coordinate of the point of the triangle visible in this pixel is computed. This is the same as ray triangle intersection, and the triangle's z-coordinate is compared to the z-value stored in the z-buffer at this pixel. If the triangle's z-coordinate is smaller, then the triangle point is closer to the front clipping plane at this pixel than any of the triangles processed so far, so this triangle's color is written into the frame buffer and its z-coordinate to the depth buffer. Thus, the frame buffer and the depth buffer always store the color and depth of the triangles which are visible from the triangles processed so far. Projected triangles are rasterized by visiting scan lines and determining the intersection of this horizontal line and the edges of the triangle. Pixels that are in between the x-coordinates of the two edge intersections are those where the triangle is potentially visible. Pixels in this row are visited from left to right, and the z-coordinate of the triangle point whose projection in this pixel is calculated. This z-coordinate is compared to the value of the depth buffer. So the first question is how the z-coordinates of the triangle points are computed for every pixel of coordinates x and y. The triangle is on a plane, so x, y, z coordinates satisfy the plane equation, which is a linear equation, so z will be also a linear function of pixel coordinates x and y. The evaluation of this linear function requires 2 multiplications and 2 additions, which are too much if we have just a few nanoseconds for this operation. So to speed up the process, the incremental principle can be exploited. As we visit pixels in the order of coordinate x, when a pixel is processed, we have the solution for the previous pixel. It is easier to compute the increment than obtaining the z-coordinate from scratch. Indeed, the difference between the z of x plus 1 and the z of x is just a constant, which is called here by a. Such an incremental algorithm is easy to be implemented directly in hardware. A counter increments its value to generate coordinate x for every clock cycle. Simultaneously, a register that stores the actual z-coordinate in a fixed point format is updated through an adder, so it is increased by constant a for every clock cycle. The final problem is how z-increment a is calculated. One way of determining it is to satisfy the interpolation constraints at the 3 vertices. The other way is based on the recognition that we work with a plane equation where x, y, z coordinates are multiplied by the coordinates of the plane's normal vector. Note that the coordinates of the screen space normal are needed not only here, but also in backface calling. So in this operation called triangle setup, we decide whether this face is a front face or a back face, in addition to calculate A, which is the increment of the Z-buffer algorithm. Backface calling and Z-buffer algorithm are executed by the GPU in its fixed function pipeline. We can enable or disable the operation of different hardware units. If we want to use Z-buffering in GLOT init display mode, we should specify this option to allow the GPU to allocate some memory for the depth buffer. Then Z-buffering can be enabled with the GL-enable GL depth test function and disabled with the GL-disabled GL depth test function. Similarly, we can enable or disable backface calling. If we use depth buffering, the initialization of the Z-buffer should be done at the beginning of each drawing cycle by telling GL-clear that not only the frame buffer, but also the depth buffer should be initialized. When a triangle point turns out to be visible, its color should be computed and written into the frame buffer. According to physics, the color is the radiance calculated in the direction of the eye, which is the sum of the contributions of abstract light sources in the local illumination model. For a single light source, the radiance is the light source intensity multiplied by the BRDF and the geometry factor. In incremental rendering, we try to reuse calculations done in a pixel, so the evaluation of this formula for different pixels shares computations. For example, we can evaluate this formula only for the 3 vertices of the triangle and apply interpolation in between the triangle vertices. This option is called per-vertex shading or Garrod shading. Or, while the illumination formula is evaluated at every pixel, at least the vectors needed for the calculation are interpolated from the vectors computed at the vertices. This is called Fonck shading, or in other words, per-pixel shading. Let us see per-vertex shading. The radiance can be computed in vert coordinates, since here we have everything together needed by the illumination calculation, including the illuminated objects, light sources, and the camera. Alternatively, radiance could also be computed in camera space, since the illumination formula depends on angles and distances, and the transformation between vert space and camera space is angle and distance preserving, or congruence. So we would obtain the same results in both coordinate systems. However, radiance computation must not be postponed to later stages of the pipeline, since the mapping to these coordinate systems may modify angles, so the result will not be valid anymore. After tessellation, the object is a set of triangles with vertices and shading normals. These are transformed to vert space by multiplying the vertices with the modeling transform and the normals by the inverse transpose of this matrix. So our triangle arrives in vert space. In vert space, the view and light directions are computed at the triangle vertices. If per-vertex shading is applied, these vectors are immediately inserted into the illumination formula, and we obtain the reflected radiance at the vertices. The triangle vertices with their computed colors are mapped to screen space, where the triangle is rasterized. The color of the internal pixels is computed by interpolation of the RGB values of the colors at the vertices. This is very similar to the interpolation of the depth values. Let us see the vertex shader of the per-vertex shading approach. As its name suggests, illumination computation takes place here in the vertex shader. Uniform parameters include the transformation matrices like the modal view projection, modal and inverse modal transformations. Modal view projection matrix takes the point from modeling space to normalized device space. M, the modeling transformation, takes it to world space for illumination computation, and its inverse is used to transform the normal vector. As illumination happens in world space, the shader also needs the material properties and light source parameters, as well as the position of the eye, which is used to determine the viewing direction. These are the uniform parameters of the vertex shader. As for varying inputs, the position and normal vector associated with the vertex arrive at input registers 0 and 1. First, the point is transformed to normalized device space and written to the GL position output register, as almost always. The remaining part of the shader computes the reflected radiance. The point is transformed to world space, where it is called W position and is in homogeneous coordinates. Illumination direction points from the shaded point to light source position. If they were in Cartesian coordinates, the difference of the two vectors should be obtained. However, they are in homogeneous coordinates and can even be ideal points being at infinity. If they are not ideal points, homogeneous division would convert homogeneous coordinates to Cartesian coordinates, so the difference could be computed. As the difference is normalized later on, we can multiply the two vectors by a scalar. The resulting L illumination direction would not change. Let this scalar be the product of the two force homogeneous coordinates. So we can get an alternative and also valid expression for the illumination direction. The advantage of this alternative formulation is that it is valid even if the points are at infinity, so one of the force homogeneous coordinates is 0. Thus we can handle point light sources and directional sources in the same way, just directional sources must be placed at ideal points. Vector V is the viewing direction, which is obtained as a difference of the position vector Wi and the position of the calculated point, having converted from homogeneous coordinates to Cartesian coordinates. The normal vector is transformed to world space. However, while points are transformed as multiplying their row vector with the transformation matrix from the right, normal vectors are column vectors that are transformed with the inverse matrix being on the left. Half-wave vector H is computed as adding the unit vectors L and V. The geometric factor is the cosine of the angle between a normal vector N and illumination direction L. If this is negative, the result is replaced by 0. The Fonglin specular reflection also needs the cosine of the angle between the surface normal and the half-wave vector, which is obtained by another dot product as these vectors are normalized. Finally, the ambient plus diffuse plus specular reflection model is evaluated and we assign the result to the reflected color. This reflected color is an output variable of the shader. The fixed function elements interpolate the color variable for internal pixels, which is written into the frame buffer without any modification in the pixel shader. Gouraud shading produces satisfactory results if the surfaces are finely tessellated and not too strongly glossy or specular. If the triangles are large and the material is highly glossy, the highlights will look strange and deformed, revealing the underlying triangular approximation. The problem is that the glossy reflection is strongly nonlinear, which cannot be well represented and approximated by linear interpolation. The solution to this problem is Phong shading, which interpolates only those variables which are smoothly changing inside the triangle. Phong shading interpolates the vectors, like the normal vector, view vector, and illumination vector, and evaluates the radiance from the interpolated vectors at each pixel. The triangle vertices and their shading normals are transformed again to word space. Here, illumination and view directions are obtained for each vertex. The vertices are transformed further to screen space, and the computed normal, illumination and view directions will follow them, but without any transformation or modification, so they still represent word or word space locations and word space directions. These vectors are interpolated inside the triangle for every pixel, where the radiance is obtained with normalizing the vectors and evaluating the illumination formula. In Phong or per pixel shading, the vertex shader prepares the vectors needed by the illumination formula and outputs them in output registers W normal, W view, and W light. In addition to the usual task of transforming the model space location of the point to normalized device space and writing out the result into the GL position register, preparation includes the transformation of the point to word coordinates and the computation of illumination and view directions. Again, we can use the trick introduced on the previous slide, which enables the uniform treatment of point and directional light sources. The normal vector is transformed to word space with the application of the inverse modeling transform matrix. The pixel shader gets the interpolated output vectors of the vertex shader, W normal, W view, and W light, as well as uniform materials encoding the material properties and the light source parameters. First, the normal, view, and light directions are normalized, then the half-wave vector is computed, and finally we use the ambient plus diffuse plus specular reflection model to obtain the reflected radiance, and this reflected radiance is written into the frame buffer. NPR, also called non-photorealistic rendering, means the simulation of artistic type rendering, which simulates painting. As a painter has a limited number of paints, colors are quantized, and the silhouette is drawn in black. The silhouette is defined where the surface normal is approximately orthogonal to the viewing direction, so their dot product is close to zero. So using the same vertex shader as was introduced with Phong shading, we can implement an NPR rendering by modifying the pixel shader. As before, vectors are normalized. We quantize the geometric term into two levels, assuming that the painter has just two paints from every color. Here, we decide whether the point corresponds to a silhouette or not, and if it corresponds to a silhouette, the output color is black. Otherwise, we use the diffuse color, the own color of the surface, modulated by the quantized geometric factor. The result is shown here and compares the result with Phong shading and another special version of Phong shading where the surface normal is also modulated either procedurally or according to a texture. This is the UML class diagram of a simple 3D engine. Our virtual world is an object of type scene, which can be animated and rendered. A scene has arbitrary number of light sources and a single camera. and a heterogeneous collection of objects, geometric objects. An object has animation parameters, determining scaling, translation, and rotation, and can be animated by setting these animation parameters, and can also be drawn with the help of OpenGL and the GPU. Of course, the specific way of drawing and possibly animation is object type dependent, so these virtual functions are redefined via inheritance. For drawing, an object needs material properties, texture, a geometry typically encoded in a vertex array object, and also needs a shader that specifies how the vertices and the pixels are calculated while this object goes through the rendering pipeline. As many objects may share the same shader, material, geometry, or texture, objects do not contain these properties, but they are associated with them. It means that the application creates shaders, materials, textures, and so on, and every object can pick from them according to its own taste. The relation of the shader and the object needs special attention and care. Object properties, apart from the vertex data, should show up as uniform variables in the shader. The question is, whose responsibility should be this copying? If it is the shader's responsibility, the object structure becomes rigid, and it would depend on the shader. If it is the object's responsibility, the shader cannot be changed without the modification of the object. Thus, we introduce a kind of communicator object called the render state in between the shader and the object. Objects fill up the render state as objects may wish, and shader fills up its uniform variables based on the content of the render state. A scene has a camera, a heterogeneous collection of objects, a light source, and it also defines this render state. Rendering means the initialization of the render state based on the parameters that are available directly from the scene, and then calling every object to draw itself based on the already initialized state. Object is associated with a shader, a material, a texture, a geometry stored in a vertex array object on the GPU. An object has animation parameters that can be used to compute the scaling, translation, and also the rotation. During rendering, the modeling transformation M is set based on the transformation parameters, and its inverse is also calculated because this inverse will be used to transform normal vectors. Material and texture are also set. The shader's bind function activates the data of the state in the uniform variables of the shader. And finally, the geometry's draw function triggers the rendering pipeline to process the vertices in the VBOs of the VAO of the current object. A shader gets the source codes of the vertex shader and fragment shader programs, compiles and links them, and makes them active on the GPU. This simple example shader draws everything in black. The vertex shader transforms the points with the MVP transformation matrix from modeling space to normalized device space. And the fragment shader colors every pixel that corresponds to the given object with black color. As this vertex shader has a single uniform parameter, the MVP transformation matrix, the bind function of the shader calculates this MVP matrix from the render state and activates it in the GPU. Such shaders can be used to render shadows projected on surfaces, planar surfaces.